Welcome back to .NET Rocks. This is Carl Franklin.
And this is Richard Campbell.
And just before we take off for Prague here.
Well, I'm already in Moldova, so just to make things weird.
Just to make them weird.
Well, we're used to being in separate locations where we record together, but...
How's Moldova? I know this was on your bucket list of places to go.
Well, I'm keen on any country I haven't been to. Moldova sits between Romania and the Ukraine. Mm-hmm. And is a landlocked country, sort of. There's a big river that connects it to the Black Sea that's navigable. Uh-huh. It's wine country, and they make an astonishingly good brandy called Divan that I've been a fan of for many years. So that's been an excuse to drink a little Divan and to hang out in a place where the vegetables are fresh, and everybody's uncle has their eggs and right. Things like that. So it's been very enjoyable. Did a great show, did some winery tours, and I'm going to tomorrow. So it'll be, if I never make another thing, at least we'll get the episode 1600 out. But tomorrow I'm going to go to the Transdniester region of Moldova, which is the eastern side of the Dniester River, which is a breakaway province of Moldova that is sort of keen on the old Soviet system. So we've got a tour group. It's going to be an interesting experience, but everybody's description of it is you're about to jump back 30 years.
Wow.
So, I'm sucker for an experience, man. Anything like this to sort of get a view of how folks are. And I was at a code camp on Saturday and met several people from the Transdniester region that were at the conference. So they were like, oh, no, you have to come. I'm like, yeah, I'm going. I got to see this.
Wow. That sounds fun.
It's strange, but it's fun.
Well, we're going to record a few shows from Update.net in Prague. Mm-hmm. And that's going to be a lot of fun.
Yeah, no, I'm looking forward to it.
Yeah, I'm looking forward to hanging out in the Czech Republic. All right, man, let's roll the music because I have a really cool website for Better Know Framework. All
right, dude, hit me.
Well, sometimes there are games that you play in the browser, and sometimes you write code in the browser. Mm-hmm. Sometimes you learn code by going to a website. This kind of combines all of those things. It's called Code Combat.
Okay.
CodeCombat.com.
So it's a game that you write code in?
It's a game that teaches you how to write code. Yeah. And it's graphical. So you start at a certain level where you get basic syntax and all of this stuff. But it's all swords and weapons, and you choose a hero and you choose a language. Python is the default, but you can also learn JavaScript or CoffeeScript.
Okay.
Interestingly. And you choose a persona, and then you go through all of these different challenges, and you move through, in level 1, it's like a castle, and, the classic kind of web arcade game things are there. It's pretty cool.
That's really interesting. What a fun way to teach coding.
Yeah, I can imagine, you got your 13-year-old kid who is playing video games all the time and, is thinking about writing code, but, would rather play video games. And you can kind of do both at the same time.
Oh, and there's a whole section here specific for teachers, too. So you can make it classroom curriculum.
Yep.
That's really neat.
And, the thing I don't know is I haven't played. So as a game, I don't know how fun or not fun it is. But to tell you the truth, just looking at the graphics, it looks kind of fun.
Yeah, nice visuals.
Nice visuals.
That's cool.
That's it. CodeCombat.com.
Nice find.
So who's talking to us today, Richard?
It's always fun to dig through the Geek Outs for some different comments. And I'm going a little far back. This is from episode 1091. So 500 or so shows ago. This is from the Water Power Geek Out, January of 2015. And that, is mostly about hydroelectric power.
Right.
But also some good tidal and wave power stories, too, as you recall.
Right.
Which I think fewer people knew much about. And this comment comes from Mike. He says, after having taken a break from your show during most of December due to not having commute into work. And listen, Mike, that's just not trying hard enough.
Yeah, that's no excuse.
It's not just the commute you can listen on. Maybe you walk the dog, or you work out, or you mow the lawn. I know some folks who, while they're listening, they listen to the show while they're washing dishes.
Do you wash dishes, Mike? Be honest.
Yeah, you could be washing dishes while listening to the show. Just saying. Yeah, I get it.
Try a little harder, Mike.
Yeah, try a little harder. Come on. Anyway, Mike goes on to say, I've just managed to catch up and be current. 3 weeks of listening to you two, and admittedly this is 4 years ago, right?
Yeah.
And the guests chat has made facing public transport so much more bearable. So thank you.
Good.
It's very interesting to hear what's happening in other countries while I'm being in the UK, as the power companies based here seem to be very much in the pocket of government, and innovation in areas other than marketing and accounting don't seem to be on the agenda. Which is a fairly cynical comment because, I'm always taking notes of what's going on the energy world these days. And, the last year in 2017, the UK had a breakthrough. The United Kingdom pretty much invented production electricity. On the week of April 2017, the UK had its first 24-hour stretch of power generation using no coal for the first time in 135 years.
Wow.
AKA, since the time when coal was used to make power, the UK has had coal power plants making power.
At least for 24 hours in a row.
Yeah. It's just that the power levels were such that they were able to use other sources. So the UK is making a transition away from coal-powered energy. Half of their power is made from natural gas, so they're still burning stuff.
Right.
It emits less carbon dioxide and toxins than coal, but it's still not the cleanest one. But the other half is nuclear power and renewables, wind and wave, solar, and tidal flow energy.
Right.
So I wouldn't discount the ability of the UK to actually move in this particular direction. They've got some also in May. This is also in my notes. They turned on 32 turbines, wind turbines in Liverpool Bay, and these were from the MHI Vestas. These were 8 megawatts each.
Wow.
They're 640 feet tall, 262 foot long blades on them. One revolution of an MHI Vesta is enough power for a house for 29 hours.
Wow.
Like, they're beasts.
Yeah.
So don't give up on your country just yet, dude. Like, the UK is making progress. And I'm not going to argue with you that the power companies are pretty tightly tied to the government, because they kind of need to be. Power is a utility. It's not a free market product, because you can't choose as a consumer not to use it. It's like, I don't like your prices today. No electricity for me.
Right.
We regulate electricity because we consider it an essential service, part of our society. And so we try and keep the rates fair and the services fair. And the way that you improve power, if you see that necessary, like having it more ecologically sound, is you press against your government for it. You write to your MP. And if necessary, you march and you sign petitions. And that's what's happening in the UK.
Yeah.
And the results are substantial. So, Mike, thank you so much for your comment. A copy of Music to Code By is on its way to you. And if you'd like a copy of Music to Code By, write a comment on the website at .netrocks.com or on Facebook. We post every show there every week, actually, twice a week. And if you comment there and we read it on the show, we'll send you a copy of Music to Code By.
And by the way, Music to Code By now up to 18 tracks. I just added 3 to the complete collection, which the price is only $42 now.
Nice.
And so 18 tracks for $42, because you know why? 42 is the answer to everything.
Life, the universe, and everything.
Yeah, that's right.
Awesome, dude. That's a lot of tracks.
Yeah, and I think it's going to stay at $42 for a while.
I don't know how you get the creativity to keep coming up with new sounds that get us into the flow. It's impressive.
Nothing is more fun than spending a Sunday afternoon making a new Music to Code By. It's just,
you must enjoy it. You
so
keep
much
doing
fun.
it. Awesome.
Yeah, it is. And then I enjoy coding to it, which is even better.
A consumer of your own product.
That's right. I gotta be. And also follow us on Twitter. He's at Rich Campbell. I'm at Carl Franklin. Send us a tweet. We wave them goodbye.
Oh, I got to tell you something terrible.
What?
I found a picture of a mug that's got some code on the side of it that says, if and it's like a coffee mug icon is full, then keep coding, else fill coffee mug.
It's so bad.
I'm telling you, it's like one of the most retweeted things I've ever done.
Oh,
now
really?
People are arguing over the code, and it's like somebody's complaining because it's coffee that I've actually put Java on the side of the mug. That's what that is. Okay.
You know, the next step, right? You're going to have Velvet Elvis paintings up in your home, and everybody's going to want to come to dinner.
I think somebody was complaining because the curly braces were on their own lines, and that's just wrong. That's what that is. Hey, happy 1600th episode, my friend.
You too. This is, we usually make a big deal on the 100s, but, we just decided to do a Geek Out and just quietly go about our business because, we've done that.
Yeah, well, this episode happened to fall on the third Thursday of the month, which is where I would normally put a Geek Out. So it just sort of worked out that way.
Yeah. Well, it's early in the morning here, sir. Otherwise, I would have a scotch and toast in your direction. But we will be together soon enough in Prague, and I'm sure we will celebrate there.
Awesome.
So, superconductivity. What's new, man?
Well, it's interesting. There's a lot of new science still going on in there. I've been avoiding this subject, to be perfectly honest, and one of the reasons is that I've stepped in problems around electricity before. If you recall back, one of our earliest Geek Outs, when we started talking about alternative energy, was the electricity Geek Out, which was episode 732.
Right.
That's really quite a long time ago, 732. And there I was trying to explain, I grew up understanding electricity. My father's in electricity.
Right.
And so but I resisted all of my assumptions and read a lot of the latest thinking about electricity and talked about it. And that upset folks because they were taught very much the classical science of electricity. And I talked about it that electricity is not just a flow of electrons. Electrons only move so fast and power moves faster than that there's this idea of quanta or photons actually moving around as well. And I resisted calling them photons for the simple reason that immediately people think light. And photons are not necessarily light. One particular spectrum of photons are.
Okay.
But X-rays are also photons, and radio waves are also photons. We forget.
And those aren't in the visible spectrum.
They're just not in the visible spectrum, but they are a part of the electromagnetic spectrum.
Yep.
And heck, in 2012, when we did that show, we did that show in 2012. I was still pretty naive. I've read so much more in this space and just realized, the correct answer is even more complicated. Electricity's been around since the mid-1800s. And most of our understanding of electricity comes from folks like Maxwell and Lorentz and Faraday, who were doing empirical measurements of electricity. So they may have not understood all the details of atomic theory. In fact, atomic theory would come later. But they were able to derive equations to help us be able to build things like transformers and radios and motors and so forth. You didn't have to have all that the details of how everything works. So in the area of classic physics, electricity works a particular way that can help you. But if we're going to talk about superconductors, it's not enough.
Yeah.
Those equations, I look at them the same way I look at Newton's equations for gravitation. So we were able to model our solar system using Newton's equations. But it wasn't until Einstein came along with special relativity that we got finer detail. And we rely on special relativity all the time now. GPS wouldn't work without special relativity.
Whoa, so Einstein, without him, we wouldn't have GPS?
It just would be inaccurate because we actually have to compensate for distortions in space-time for the GPS satellites. Like it's a measurable number that renders GPS signals inaccurate if you don't adjust for special relativity.
Special relativity, the gift that keeps on giving.
Well, special relativity is part of how electric fields work too.
Yeah.
The relative motion between a stator and a rotor in a motor is affected by special relativity. We don't have to go into the details of that if we don't really want to. But quantum electrodynamics is a key part of understanding how superconductors work. You can deal with regular electricity fairly well with classical physics, but we've had a tough time explaining superconductors because of all of the quantum effects that are going on in there. And I've read enough quantum electrodynamics now to be clearly where Feynman told me I'd be, which is if you think you understand quantum mechanics, you don't understand quantum mechanics.
So it's just that we can observe things and we know how to change inputs to achieve outputs that we want, but mechanistically it's still very hard to describe what's going on in there.
Well, and that's why we are still discovering new things about superconductors empirically, as opposed to having a model that works so well that we should be able to say, given this model, these ingredients should make a superconductor. We're still not there. We still are literally mixing and mashing. You know, and if you think back to like the energy storage Geek Out, most battery designs are empirical too. We do not have great models for how electrical storage works. We have empirical models based on what we've done, but the exact amounts of cobalt to put into a lithium polymer battery, that's still a bit of witchy science.
Yeah, we still don't know a lot about how life works in general.
Yeah, we're still figuring all of that out.
Yeah.
So before you can dive into superconductors, you kind of have to talk about conductors.
Okay.
All right. Because we know there's certain elements that conduct electricity better than others. But every material has a certain amount of conductivity and a certain amount of resistivity. And, you know, just to make it extra fun, the materials we usually use for conduction, things like copper and iron and aluminum, aren't good candidates for superconductivity. Like, how strange is that? That you just think, we call it superconductivity, it should just be more. So shouldn't a conductor become a superconductor?
Right.
No, it doesn't work that way.
So I guess it's how it behaves at lower temperatures that makes the difference, right?
Well, that's what we found so far. And certainly that's where this story of superconductors begins.
Okay.
Back in 1911, a fellow by the name of Heinke Owens was doing experiments with mercury, and he had been measuring. He'd cooled mercury down enough that it was frozen, so it was now a solid. It's normally liquid at room temperature. He was passing electricity through it, and he could measure that the resistivity of the mercury was descending as it got colder.
Yeah.
Now, arguably Owens' greatest invention is actually the helium cooler. He was one of the first people to ever figure out how to cool helium enough to make it liquid. And this is a fairly tricky refrigeration cycle. Helium is a noble gas, and it's tough to handle. It's easy to leak. And so he would repeatedly compress the helium, which makes it hot. And then he would chill it with liquid nitrogen. So using a heat exchanger, and then he would expand it, which causes it to cool even further. And then he'd repeat the cycle until he got to the point where he actually had helium into a liquid form.
That's what I like about helium. It's noble, but it's not pretentious.
It reminds me of a couple of wines I've had. Yeah.
Yeah.
Anyway, he was making these measurements showing the resistivity of the material going down. We know that the mechanics of resistivity comes down to an intrinsic resistance within the material itself. And that's an interesting conversation of how we determine that, and where what a bunch of quantum stuff is going to show up. The length of the material increases as it gets longer. The cross section, if it's wider across, it's actually less resistive. And the temperature. And so he was able to control the temperature. So he was lowering the temperature. And as his curve, he had a nice curve going, and at the current gradient of the curve, it was going to hit absolute zero before it ran out of resistance.
Yeah.
But at 4.2 degrees Kelvin, now the Kelvin scale is absolute zero is at zero.
Yeah.
Which is negative 273 degrees Celsius or negative 460 degrees Fahrenheit, aka cold.
Kind of want to put on some sweaters.
Yeah, wear a coat.
Just thinking.
A little chilly.
Wear your mittens.
But at 4.2 degrees Kelvin, suddenly the resistance in the mercury stopped. It just went away.
Whoa. Just stopped?
Yeah, they suddenly was no resistance at all.
No resistance.
Yeah.
Wow.
So it was a perfect conductor, and that was a surprise. It wasn't especially useful, but again, he was doing empirical science, but he did find, hey, with mercury, this happens. And it kicked off a whole bunch of supercooled experiments, and they found that a bunch of elements do have this effect, that they go to superconductive states. when they get extremely cold. In fact, mercury was one of the warmest superconductors at 4 degrees. Lead was like 6 degrees, easily the warmest of them all. But they were all extraordinarily cold.
Wow.
If not particularly useful.
And Richard, hold that thought right there while we take a moment for this very important message.
Hi, this is Richard. The Dev Intersection Fall Show this year will be December 3rd to 6th in Las Vegas at the MGM Grand Hotel. The lineup is awesome. Scott Guthrie, Scott Hanselman, Scott Hunter, yes, all the Scotts. But also a ton of great industry speakers for some insight on what's coming up in the world of .NET. You know, Core 3 is bringing client technology like WinForms and WPF into play. Could it be time to migrate your existing desktop apps to this new technology? Come learn more at Dev Intersection, December 3rd to 6th in Las Vegas at the MGM Grand. Go to devintersection.com to register and use the code .NETROCKS to get a discount.
And we're back. It's .NET Rocks. Carl Franklin, Richard Campbell. Richard's talking about superconductivity, and you were just talking about the point at which mercury becomes completely resistance-free.
Right.
And lead. Some of these other things.
Other these single elements. So none of them particularly useful, but we had this interesting phenomenon that we didn't have a good explanation for. We didn't quite know why the materials did this. We did know that they had to get extremely cold. It's not until the 1950s that we actually get a model of why superconductors superconduct. And it's known as the Bcs Theory, after the initials for John Bardeen, Leon Cooper, and John Schrieffer. And John Bardeen is the same John Bardeen who will go on to be part of the team that makes the first transistor. So, you know, great material science guys. And they will ultimately get a Nobel Prize for this in the 70s. But they start to model the idea of what goes on inside of a wire in normal conductive states, and then how superconduction comes on. Again, this is a model, you know. Some would say in science, this is the lies we tell children to make it easier to understand.
Right. It does make it easy. And you have to explain things in an easy way, or else we won't be compelled to learn the rest of it.
All right. So we're going to talk about an alloy of niobium and titanium, which is one of the most popular superconductors today. It's still, at room temperatures, it still acts like a wire, so it's fairly easy to work, which is one of the things that makes it so popular. And this is the superconductor that to this day is used in things like the Large Hadron Collider and most MRI machines and so forth. But I want you to picture looking at the wire at an atomic level. So it is a lattice of atoms, right? Of niobium and titanium atoms interlocked evenly, but they're all moving. They're all wiggling a little bit, right? They all have energy in them.
Right.
Now, among the atoms are free electrons. So there are valence electrons on niobium and titanium that can easily kick loose. So that the atoms are slightly positively charged because they're short an electron, and the electrons are sort of floating free in the wire. And when we add a potential or a current, the electrons will tend to flow towards the positive source of the current. Now they're attracted to the atoms because they're negative and the atoms are positive. And then the atoms are also attractive to the electrons. Now it's mostly open space, right? So the dimensionality on this is fairly tricky. But because the atoms are in a lattice, they sort of move in regular ways, and they will tend to pull as groups towards these electrons as they move by. Very small amount of movements. But these movements are somewhat synchronized because they're in a lattice. They all sort of pull together. So it's almost like they're bending the wire a minute amount. And this harmony of motion is called a phonon.
Phonon? Never heard that one before.
It's an interesting word, isn't it? But imagine that it's a point where multiple atoms are pulling together towards an electron that's in motion. And so as the electron goes by these atoms, they then sort of spring back and another set pull towards. And so these phonons are sort of a repeating pattern through the wire. And sometimes it doesn't work out. Sometimes the electron collides with the atom and becomes a valence electron again. And when it does that, it changes that atom back to a neutral atom because it has the extra electron. So it's no longer attractive.
Yeah.
but it's got a high energy state still. It probably will release a photon in the process, which might go to another electron, which will give it more energy. Or another photon will receive onto that valence electron, and it'll pop off again. And this is when we get into some more of the quantum effects, right? Like Feynman described this concept, it's, simplest way is that photons are going to go from one place to another in place and time, and electrons go to one place or another in a place and time. And sometimes an electron will emit or absorb a photon at a certain place and time. So you don't have complete consistency in all of these movements. Now, I'm jumping ahead because the quantum theories come later. But the BCS theory said that when you start to cool down that niobium-titanium combination, it makes the lattice actually change shape. So it gets a kind of regularity in the shape that doesn't stop the phonons from happening, but the phonons get into a sequence that causes the electrons to pair up as they move through the matrix. And when those electrons pair up, we call them Cooper pairs or Cooper electrons.
Now they pair up, but they're still all negatively charged. Otherwise, they wouldn't be electrons.
Yes, so they repulse from each other. They don't want to be too close to each other, but they're moving through the phonons at a spaced rate that almost gives them a regularity.
Wow.
And so there's a point where you cool the material down enough, and it hops into this, what they call a structural phase transition. So we're now understanding, and again, I'm using a little bit later knowledge, but this is what they were trying to describe in 1957, that as you get colder, this phase transition in the lattice helps organize the phonons to help the electrons go into their Cooper pairs.
Hey, maybe like Eskimos who are walking out in the cold, they try to like stay close to each other so that they, can warm each other up.
But not too close because their breath's not that good, right? Like so there's a certain distance you want between them and yet still moving. And this point of superconductivity happens when that spacing becomes perfectly even.
Wow.
And so you have this really stable flow. And so, the friction inside of a wire, the resistivity inside of a wire goes away because the electrons are no longer pulling and pushing on things, or rather they're pulling and pushing at a very consistent rate. So that's the 1950s definition of superconductors. And at that point, we did have things like niobium titanium, which is a very popular superconductor because it's ductile. It's good for making coils and things with. Now, I've avoided explaining one other complicated piece of this. That's another part of when superconductors engage, and that's its effect that it has on magnetic fields. Okay. So, niobium titanium at room temperature is not magnetic. But as it becomes a superconductor, it has an interesting effect on magnets. So normally magnetic fields will penetrate through an object. But once it becomes a superconductor, the material rejects the magnetic field. And this is where you see those levitation effects we talked about. It's called the Messner effect. Yeah,
like when you have these little, what looks like a train track, and you cool it with liquid nitrogen, you can pass a magnet around, it just keeps going and going and going. That was like the first experiment I ever saw with superconductors.
Right, and you were looking at a different class of superconductor, what they call a cuprate superconductor, which I will talk about.
Okay.
But that magnetic rejection is a unique aspect of superconductors that literally they push all of the magnetic fields away from them. So we're normally, we talk about ferromagnetic, so like iron that's naturally magnetic because of the way that its electrons are organized.
Right.
Or you have paramagnetic, which is not particularly interactive with magnetics. And then you have antiferromagnetic, where it's actually repulsive to typical magnets. The state that superconductors go into is called a diamagnetic state, which is literally I reject all magnet fields. And that is unique to superconductors, and it's a very important aspect of what makes superconductors practical for use.
That's awesome. Well, Richard.
Yeah, buddy.
Guess what time it is now?
It must be that happy time again.
Yeah, it's time to update a long, bad joke about superconductors. It's a classic. I'll do it like Henny Youngman. A room temperature superconductor walks into a bar. The bartender says, "Get out of here. There are no superconductors allowed in this bar. The room temperature superconductor leaves without putting up any resistance." Boom. See what I did there? All right, now that's awesome. A bad joke. Now let's update this joke, okay?
Okay.
A room temperature superconductor walks into a bar, but it's a Zen Buddhist bar. And the superconductor says, "Hey, if you don't give me a beer, I'm just going to dance around forever." And the bartender goes, "Om." And he leaves.
Okay, that was the good joke.
All right,
Chris.
That's a little updated.
Oh, my goodness.
See what I did there?
I see what you did there.
All right, it's actually time to give away a $200 Amazon gift card, compliments of Progress Telerik, to one lucky member of the .NET Rocks fan club. Hey, but first, let me tell you about the most comprehensive developer toolkit for building modern apps on the market today, Telerik DevCraft. With more than 1,100 Telerik.NET and Kendo UI JavaScript components and controls, you can easily build modern, high-performant web, mobile, and desktop apps, as well as chatbots. The toolset also includes reporting solutions, automated testing and productivity tools, and comes with a range of support options. New this year is a free online training program for all license holders. With this, alongside thousands of demos with source code, comprehensive docs, and a full assortment of Visual Studio templates, you'll be up and running with the Progress Telerik and Kendo UI tools in no time. Download a free 30-day trial today at telerik.com/download. Oh, and also consider supporting .NET Rocks by making a monthly pledge at patreon.netrocks.com to ensure .NET Rocks will stay on the air for years to come.
All right, buddy. Who's our winner?
Today's winner is Harper Shelby.
Congratulations, Harper.
Yes.
Golf clap for you.
Golf clap for Harper. Harper won a $200 gift card to Amazon.com. Compliments of Progress Telerik just for being a member of the .NET Rocks fan club. And if you'd like to be a member, go to .NETRocks.com, click on the big Get Free Stuff button, answer a few questions, and join the fan club. We have thousands of members all over the world, and every show we like to give away stuff from our sponsors. And every December, coming up here very soon, we give away a $5,000 technology shopping spree to one lucky member of the fan club. But you got to sign up to win.
Ask me.
What? You have something you'd buy with $5,000?
Yeah.
What?
You know how much crazy lighting stuff I've done in my house over the years, right?
Well, you like lighting and you are crazy, so yeah, yes, I get that.
Good combination. Yeah. And one of the problems I have is that I originally wired my basement with scene-controlled lighting on a system called Compose PLC.
Okay.
And then I used it upstairs as well.
Yep.
And about the time I finished the place upstairs in 2009, that line of products was discontinued. And so I bought up all the extra parts I could, and I've just been sort of functioning off that. And then we had the flood in the basement in 2015.
Right.
Which was, great fun, but they gave me an opportunity to, I have the good fortune to be married to a woman whose reaction to we have 2 inches of water in the basement is to pull out the plans and say, "So what changes did you want to make?"
Yeah, that's great.
And one of the things I said was, I want to experiment with DC lighting, right? We've done a whole Geek Out about this.
Right.
And one of the benefits of doing that is I got to scavenge all the Compose PLC that was in the basement as spare parts for the upstairs, because these light switches and things, they do wear out. Eventually they break. Some lights have worse loads than others. And so there were certain switches that were failing every year or so, and you only have so many backups. I finally found a lighting system worthy of replacing the Light-A-Lear system upstairs.
Wow. Tell.
It's taken a while, because my requirements are fairly steep. First off is I like having scene controllers in the room. So that I don't have big wall plates full of light switches. I have little buttons that turn on multiple lights when you press them.
Right.
And the load-bearing switches are actually hidden in a closet.
Yeah. Okay.
And I don't have additional wiring. Like traditional lighting systems like that have separate signaling wires between the controllers.
Right.
And I didn't put that in.
Okay.
I was in the Compose PLC. It actually uses a kind of X10 for communication. So I had, that centralized lighting, scene controls with no additional wiring. Okay. There's the Lutron company makes a line now called Casita.
CASITA?
CASETA.
ETA.
Casita. Yeah.
Okay.
And they make their switches. They're good switches. The neutral wire smart switches are about $100 a piece. So they're not cheap.
Okay.
But They understand fluorescent lights. They understand LED lights. They understand ballasted low voltage. So you literally can configure it to the type of lighting load it has. It understands scene controlling, so you can program it into groups. It uses Z-Wave as its signaling technology.
Good.
And they have great interfaces to Google Home and to Alexa.
Nice.
So you can program up scenes and then just walk in the room and say, hey, okay, Google, turn on the living room lights, and boom, they go.
Sorry if we just turned on your lights.
Yeah. Oh, shit, I just turned on mine.
It never gets old, man.
Never gets old. It's very funny. That's it.
Yeah.
So, yeah, I mean, for $5,000, you're talking 50 lights, which is probably more than I need.
Right.
But it's, like I said, it is genuinely a step forward. It's a much more sophisticated system than my old one.
Great.
Not only from a controlling perspective, but its understanding of lighting diversity. We have no more. Remember all the dimming problems we talked about in the electricity show?
Yep.
So that's all overcome with these smart switches.
That's so great.
Yeah, it's been very exciting.
That's awesome. Hey, and before we get back to the show, I just want to remind everybody that we are now in several places, not just on your podcast app or on the web. We actually have a YouTube page, and all of our podcasts are published up there. And we also are on Spotify.
Mm-hmm.
And brand new, we are on Pandora. That's right. Pandora has recently got into the podcast business, and they're using their genomic project, or the Project Genome, or whatever it is, the technology that they use essentially to bring podcasts to you that they think you would like. So we got selected out of just a handful of podcasts for their debut, their beta. And we're very, very proud of that. So check us out on Pandora, on Spotify, on YouTube, and wherever you get your podcasts. All right. So BCS Theory, phonons. My head is spinning here. Help me, Richard.
Well, and believe me, like this again was the simple explanation, right? That but it makes sense when you think about the principles of weak field theory, right? Mm-hmm. That electrons are attracted to positively charged atoms. Electrons are repulsed from each other. We have multiple atoms, so the electron's moving through it, but it's sort of a too high an energy state to actually go into orbit around these atoms. So it keeps moving. But as we cool the material down, it sort of gets to this phase transition state that allows for the electrons to move in their Cooper pairs through the wire with no resistance.
Okay.
Right. And we combine that, and it sort of explains what's going on. What's interesting is that based on the standard model, a Cooper pair is a very weak bond between two electrons at a distance. So weak that any additional energy put into that wire would disrupt it. And so part of BCS theory said, look, the highest temperature you can make for a superconductor and maintain its Cooper pairs is 10 Kelvin.
Wow.
Okay, so stunningly cold.
Yeah. Now,
that doesn't stop us from making superconductors at that point. Like if you look at the Large Hadron Collider, which is using niobium titanium alloy, it works. They've got 1,200 tons of that.
Wow.
Pumping. They move photons around the Large Hadron Collider at 3 meters per second lower than the speed of light. Right? Like they're moving. It's like 297 million meters per second. So 3 meters per second under the speed of light using those superconductors, right? The ITER fusion project is going to use that kind of superconductor as well.
Right.
And here's where we get into the problem. In the 1980s, we come up with a new class of superconductors that break these rules. If the Cooper pair rule is important, then we can't be above 10 degrees Kelvin. But in the 1980s, and this is what we remember, that little thing you remember about levitation and so forth, because we were teenagers in the 80s.
Yeah.
There was a couple of fellows from IBM Zurich, a guy named George Bednorz and Carl Muller, who were experimenting with semiconductor oxides. And their original experiment uses lanthanum barium copper oxide.
Huh.
And it becomes superconductive at 35 degrees Kelvin. They were still using liquid helium, but it was now so much warmer that it just sort of poked a hole in the BCS theory. It's like, wait a second, that's not right.
Wow.
And end up actually spawning a whole class of what they call cuprate superconductors, or REBCO, for rare earth barium copper oxide superconductors.
So I got to imagine the people who had bought the earlier technology, like you and your lighting system, were like, damn, I should have waited.
Yes and no, because the material is a kind of ceramic. So it's quite brittle. So it's not metal. It's not a wire. If you're going to make coils out of it, it's very challenging to do that. Wow. But the more important thing that happens in that middle 80s with this set of experiments is they finally find a combination through experimentation. This is yttrium barium copper oxide that superconducts at 77 degrees Kelvin.
Wow.
And why is that important? Because that's the boiling point of liquid nitrogen. So suddenly the cooling system gets dramatically simpler if we can use liquid nitrogen to run our superconductors versus liquid helium. Right. Most technology ideas that want these ultra-powered magnets just are not sustainable when you need to use liquid helium.
Right. Okay.
So it opens the door. The trick, of course, is now we get into the materials science, the materials engineering side, which is how do I actually make this into a usable material?
Right.
You know, even back on the older styles of superconductors, there were other niobium alloys. There's niobium tin. And niobium tin actually is a much more effective superconductor. It'll actually handle much larger magnetic fields than niobium titanium. The problem is, again, it's brittle. So if you want to make it you can't really make it into a coil. They figured out a way to do it where they would actually alloy it differently, wind it into the coils so they got it the shape they want to, and then use a chemical reaction to put the tin in. So that it actually became the material necessary to make the superconductor, but you didn't have to move it at that point. It was already in the right shape.
Yeah.
But these are the experiments that took time. So after the 80s, as we saw the potential of these semiconductor oxides, they came up with new ways to make it. And ultimately, the crazy part is today, you can literally buy a spool of REBCO tape. So it turns out it'll superconduct with a very, very thin layer, basically mounted on a polymer film. So that you can wrap it around things. But because it's flat, it's planar, it has to be used in certain shapes. So we're now starting to make REBCO-based superconductive motors where the magnetic coils, instead of being a cylindrical coil like you're used to or a toroid like a donut coil, they look more like racetracks. They're flat. Wow. And they wind around each other. But they're superconductors, and they run at these higher temperatures, so they've got a lot more potential. And we can really start experimenting with different kinds of products. So, what do you think the most popular superconductive product is today?
I imagine it's a child's toy, like a science experiment kit or something.
Generally speaking, liquid nitrogen and children should not be mixed together.
Well, not the children that I know, anyway.
It's the MRI machine.
Okay, sure.
Yeah, MRIs
that makes sense.
use superconductors. And in fact, most MRIs, the vast majority, do use liquid helium too. They're using niobium titanium windings, and they're cooled with liquid helium, and they create these massive magnetic fields. You know, traditional magnetic fields are fractions of a Tesla.
Yeah.
You know, we used to mostly use the measurement Gauss to measure magnetic fields.
Right. And
you would talk about a few hundred Gauss or less than 1 Gauss. A Tesla is a 10,000 Gauss.
Wow.
With an MRI machine, the typical common MRI machines today are between 1.5 and 3 Tesla strength fields, which is why you can have nothing metal in the room.
Right.
You can wear nothing metal on your body when you go into one of these machines. But the strength of the Tesla field basically determines its ability to measure down to the cellular level in your body.
I remember a guy who had an aneurysm, a brain aneurysm, and he had to have a metal clip put in his head, and he can't have an MRI because of that.
Nope. It'll rip it right out of his head, and that won't be good. And in fact, most of the time now when they do those blood vessel enclosures, they use a plastic.
Yeah.
Because they don't want to eliminate your ability to use the high-powered magnetic fields.
Right.
They're starting to experiment. Multi-Tesla fields are so powerful that they will even destroy superconductors now. And then one of the reasons to start experimenting with Rebco class superconductors is they can handle much higher strength Tesla fields. The record now is 1,200 Tesla.
Wow.
And there are classes of MRIs coming along that are running in the 7 to 10 Tesla range. Now, those are really research models, and that the whole trick here is that you now have a magnetic field so powerful that you can measure the individual motion of iron atoms in your cells. So we're able to map out in detail every cell in your body with an MRI, which is why we're able to see things like multiple sclerosis lesions and other illnesses. That's the power of that device. But if you talk about sort of classical superconductors, they're not very popular, but they're interesting. It's the Maglev Train. Everybody loves a good Maglev Train. Right?
Maglev Train, yes.
Yeah.
Magnetic levitation, right?
Right. And now you don't have to have a superconductor to make a Maglev Train. They were building them before then. And the advantage of the Maglev Train is no rolling friction. It's literally floating over the tracks. So speeds of 300, 500 miles an hour are achievable.
Yeah.
They can't go as fast as an airplane because one of the airplane's big advantages is it flies in the higher part of the atmosphere. When you're flying at 35,000 feet, you're simply moving through less air. So you consume a lot less energy to move through the air at that altitude. Trains don't have that option. So it's only in sort of medium distances where the Maglev train makes sense. They also have tricky failure modes. If the magnetic field collapses for whatever reason, the train's going to land on the tracks. Yeah. So you better have, deceleration strategies.
Yeah.
But there are a few Maglev trains out there today. China has built a few of them. And there are experiments with Rebco-based magnetic fields cooled with liquid nitrogen.
So does Elon Musk's Hyperloop use this magnetic levitation?
Elon's original paper about Hyperloop, when he wasn't going to build it, but he was angry with what California was doing with a quote-unquote high-speed train going up the coast, and that they're actually building and will cost something like $100 billion over 20 years to build. And he said it's not high-speed and it's not cost-effective. His original design did not use maglev. He had the idea of partially evacuating the tubes and then putting a fan in front of the train to draw the remaining air and use it as an air bearing to lift the train off the tube.
Wow.
Now, which is a cool idea that I don't think actually would work. But anybody who's actually trying to build the Hyperloop has said they were going to use maglev. Nobody's done it.
Yeah.
Everybody that's built experimental scale Hyperloop trains has just put them on rails.
Okay.
So they're just wheels on rails in an evacuated tube. And even then it has an advantage because there's less air friction.
Yeah.
Right. You're not pushing against the air to move the train forward. You still have rolling friction. But if they really wanted to go to maximum efficiency, they would set up a maglev system. And ideally that maglev system would have Rebco coils in the train pressing against some kind of ferromagnetic rail. So the rail would be cheap and the expensive superconductive part would be part of the train. But those are tricky to make stable. It's actually easier to make the track the superconductive part. The problem is then you're pumping liquid nitrogen over the entire length of the track.
Right.
And that's incredibly expensive. So it is tough to figure out a great maglev solution. And maglev's awesome when you want to go fast. Everything gets harder when you want to slow down, change tracks, and let people get on and off. So you actually you're now talking about having two drive systems, a wheel-based drive system when you're moving slowly, switching, loading and unloading, and then you go over to maglev to accelerate up to your high speeds. It's doable. It's just not trivial. The more important aspect of that you are seeing with Rebco now is bigger or more efficient motors.
Huh. And we're talking just regular motors?
Regular motors. So for a naval ship, for example.
Huh.
When you want the performance, and you don't really care about the cost, right? So good military application. Right? You're able to refrigerate with liquid nitrogen, so the cost of that is relatively low. These are big motors. So
Okay.
The 20 to 40 megawatt class electric motor. If you make you can make those in traditional motor designs, and so those are already known sizes. The superconductive versions of them tend to be quieter, about 1/3 smaller, about 40% lighter, but they also have a higher net efficiency.
Wow.
Because they have so little friction, they consume less power.
Can you imagine the Segway you could build with one of them babies?
It's a monster, dude. But your trade-off is, of course, you have the cooling system, right?
Right.
So the cooling system consumes a certain amount of electricity, but you're saving electricity with the reduced friction. So the best of the large-scale motors, so a motor for a ship or for a locomotive, they run at about 97% efficient.
Okay.
Experimental versions of Rebco superconductor motors run 98.7% efficient.
Oh.
Now, that doesn't sound like a lot until you flip the numbers around. 3% inefficient versus 1.3% inefficient. So you're cutting efficiency losses in more than half with those motor designs.
And it's going to be big. I mean, obviously, I'm joking about but you're not going to see it in a Tesla, for example.
Well, we could make smaller versions. The question is it worthwhile?
Yeah. For that amount of gain.
Well, because the chiller is always got a certain amount of energy consumption and a certain amount of space. So the chillers make a lot more sense when the motors get larger. They get a little more tougher when we talk about car size.
Yeah. Okay. It's pretty cool.
Yeah. Let's punch one more hole in it because you wanted to say, you at the top of this said, what's new in superconductors?
Yeah. What's new?
What's new? And so the Rebco model has basically disrupted our understanding of how superconductors work. The Bcs theory with the Cooper pairs doesn't explain it.
And just to recap, when did that model come onto the scene?
That was 1957, and they won the Nobel Prize in 72. And then in 86, we have the Rebcos.
Rebco in 86.
And they're now up to liquid nitrogen temperature, 77, even 80 degrees Kelvin.
Yeah, it's awesome.
And so we're now still figuring out. A couple of years ago, 2016, a group started experimenting with the idea of could hydrogen be made into a superconductor?
Ooh.
Because hydrogen sits on the left-hand side of the periodic table, right? It can be a kind of metal. The problem is that it's not normally a metal. You have to put it under tremendous amounts of pressure.
And that can be dangerous.
Well, we're talking about devices like diamond anvils, where you're compressing hydrogen with 3 million atmospheres of pressure.
Oh, man. What could happen?
So, well, yeah. What happens is you break diamonds, and it doesn't last very long.
Okay.
So in experimental quantities, they used hydrogen sulfide, H2S, to make a kind of metallic behaving hydrogen that they cooled. They were compressing at 1.5 million bars, so about 1.5 atmospheres, but they only chilled it, and it became superconductive at 200 degrees Kelvin.
Oh, yeah.
You know, as opposed to the previous record, which was 77 degrees Kelvin.
Yep.
So now you're talking like negative 70, like Celsius. This is cold, but not crazy cold. But it was a gas. It was a compressed gas that they were doing this with. So they were making superconductors out of a gas. Now, admittedly, they were only making these superconductors for fractions of a second. Right? It's not easy to sustain 1.5 million bars of atmospheric pressure, but it speaks to an entirely different class of superconductive behavior. You no longer have a lattice.
Yeah.
You're literally talking about a suspended gas that undergoes the phase change, and then it allows itself to superconduct. So we're still battling understanding a bunch of key fundamentals about how superconductivity works in these quantum states. One more class of device that are much more later generation superconductive devices, and that is squids.
Squid? I ate some squid yesterday. What are you talking about?
This is not calamari. This is an acronym, superconducting quantum interference devices.
Okay.
So these are sensors you can build that are cooled with liquid nitrogen, that are their own superconductors. They are incredibly sensitive. They're a way to build lower cost and smaller MRIs. So the current MRIs that we're using today with the liquid helium are what they call high field MRIs.
Okay.
These would be small enough that you could do things like measure just a hand rather than putting the whole body in.
Okay.
We're also using squid microscopy to do analysis of superconductors themselves.
All right.
So we made a superconductor to measure superconductors. The recent experiments of measuring gravity waves depended on squids.
Oh.
So that was the actual sensor to measure photon disturbances caused by distortions in the gravitational field. And the D-wave quantum computer, which we talked about in the quantum computing show, which uses quantum annealing, actually uses squids as part of its qubit measuring system.
Wow.
And there's a project called the Axion Dark Matter Experiment.
Okay.
And axions are the current prime candidate for what cold dark matter is. This is matter we can't measure, but must exist because of the way the universe moves gravitationally.
Right.
And they have built classes of squids to actually see if they can create an interaction with that dark matter, be able to measure it.
That is so effing cool.
Yeah.
Do you think they're going to do it?
That's a good one. I mean, we've been trying to nail down dark matter for a long time.
Right.
But our ability to build better and better superconductors at smaller and smaller form factors helps us to do all that kind of testing. So, yeah, I think it's great. It's interesting to me to see sort of a few different classes of superconductor devices. Squids clearly fall in the sensor class. They were building ultra-sensitive sensors.
Yeah.
You know, the MRIs and even maglev are very much motors are about the more powerful magnetic fields we can build with superconductive.
Right.
I'd be remiss if I didn't mention at least once superconductive magnetic storage. So because superconductors don't lose power, you can create magnetic coils that you can basically put electricity into, and they'll keep the power running basically indefinitely as long as you can keep them cold. So they're only about 95% efficient, but that's better than a lot of batteries for that matter.
Right.
They're just expensive. But once you make them, and perfect them, they can store energy for a very, very long time.
And I guess, you know, what you said about military sort of leading the charge and being the customers of these things first makes a lot of sense because, you know, they need what they need and it doesn't really matter exactly how much it costs.
Yeah, I haven't dove into a bunch of the defense technologies that are using superconductors, but you can think sensors, rail guns, even EMP bombs that depend on superconductors. So the military has been spending money in the superconductor space. Yeah. And hopefully that'll benefit the civilian space at some point.
Right. Wow, that's fascinating, man. Is that sounds like the end of the show? That's
a show, right? That's an hour.
That is an hour.
You can talk about superconductors that long.
That's very cool. Well, you know, thanks very much. I always learn stuff when you geek out with me, and I hope everybody else did too.
I hope so as well. And by all means, leave us your comments. What did I miss? What would you like to learn more of? We're always looking for show ideas. And I'm not making as many of these as I used to because I am still working hard on the book. But I'm always I was keen to do one that wasn't another space show.
Yeah.
And happy to take on some other subjects. Just communicate with us.
Absolutely. And we'll see you next time on .NET Rocks. .NET Rocks is brought to you by Franklin's Net and produced by Pwop Studios, a full-service audio, video, and post-production facility located physically in New London, Connecticut, and, of course, in the cloud. Online at pwop.com. Visit our website at dotnetrocks.com for RSS feeds, downloads, mobile apps, comments, and access to the full archives going back to show number 1, recorded in September 2002. And make sure you check out our sponsors. They keep us in business. Now go write some code. See you next time.